Imagine standing at the edge of a cosmic abyss where time itself begins to dissolve. Where 1 second for you becomes 1,000 years for everyone you've ever known. Where the fabric of space stretches like taffy, and the laws of physics twist into something unrecognizable. Now imagine 3 such abysses. 3 black holes. Each fundamentally different. One weighs 5 times our sun, compact, fierce, lethal within meters. Another weighs 4 million suns, gentle at its edge, vast beyond comprehension. The third, the largest monster we've ever discovered, weighs 66 billion suns, so impossibly massive that its event horizon could swallow our entire solar system 30 times over. Here's what defies intuition. The smallest black hole would rip you apart instantly. The largest. You could fall past its event horizon and survive for hours, completely unaware you'd crossed the point of no return. The medium one? It exists in a terrifying middle ground where both fates converge. This is the gravity paradox. The cosmic riddle that challenges everything we think we understand about these objects. Because when it comes to black holes, size doesn't just matter. It completely transforms the nature of reality itself. What if the monsters we fear most are actually the gentlest? What if crossing into oblivion could feel like floating through empty space? What if everything we know about black holes is only half the story? Today, we journey through 3 encounters with the universe's most extreme objects. We'll experience time dilation that defies comprehension. We'll witness the visible distortion of space itself. We'll confront the uncomfortable truth that some cosmic deaths are instant, while others are slow, gentle slides into darkness. Prepare yourselves. We begin. In 1964, a rocket-borne X-ray detector soared above Earth's atmosphere for just 6 minutes. In those fleeting moments, it captured something extraordinary, a brilliant X-ray source in the constellation Cygnus, pulsing with the energy of 10,000 suns. Scientists named it Cygnus X-1. For 7 years, it remained an enigma. Then astronomer Tom Bolton at the David Dunlap Observatory calculated something shocking. This X-ray source was orbiting a blue supergiant star, and whatever was producing those X-rays weighed at least 15 times more than our sun. Yet it was completely invisible. By 1971, the evidence became undeniable. Cygnus X-1 was a black hole, the first one humanity had ever identified. A stellar mass black hole, born from the violent collapse of a massive star. This discovery opened a door to understanding these cosmic predators, but it raised an immediate question. If a black hole is invisible, how do we study what happens near one? To understand what happens when you approach a black hole, we must first understand what one actually is. It's not a thing, it's a boundary. A point of no return carved into spacetime itself. Every object with mass warps the space around it. Earth creates a small dip in spacetime, that's why we feel gravity. The sun creates a deeper well, a black hole. It creates an infinite pit, a tear in the fabric of reality so steep that even light, traveling at 299,792 kilometers per second, cannot climb back out. The boundary of this pit is called the event horizon. Cross it, and you're separated from the rest of the universe forever. No force in physics can save you. No engine powerful enough exists. You have left the cosmos of causes and effects we understand. But here's where size enters the equation in the most counterintuitive way possible. The radius of a black hole's event horizon, called the Schwarzschild radius, is directly proportional to its mass. A black hole of 5 solar masses has an event horizon roughly 15 kilometers in radius. A black hole of 4 million solar masses has an event horizon of 12 million kilometers, nearly 17 times the size of our sun. And TON 618, weighing 66 billion solar masses, has an event horizon that stretches 1,300 astronomical units across, 40 times wider than Neptune's orbit. What this means for anyone approaching these objects is profoundly, terrifyingly different. Here's where conventional wisdom fails us. Most people assume a bigger black hole is more dangerous. The reality is precisely the opposite at the event horizon. Tidal forces, the difference in gravitational pull between your head and your feet, depend not on total mass, but on the curvature of spacetime. And curvature depends on how compact the mass is. Think of it this way. If you're standing near a bowling ball, the difference in distance between your head and feet compared to the ball is significant. You're talking about meters versus the ball's centimeters. But if you're standing near a mountain, that same meter of height difference is negligible compared to kilometers of mountain base. A stellar mass black hole, despite its name, is tiny. Its event horizon is the size of a small city. The gravitational gradient across your body at that distance is catastrophic. Your feet, slightly closer to the singularity, would experience millions of times more force than your head. You wouldn't just be pulled, you'd be stretched into a stream of atoms, a process physicists grimly call spaghettification. A supermassive black hole like Sagittarius A* at the center of our galaxy has an event horizon 12 million kilometers wide. At that distance from the singularity, the curvature of spacetime is actually quite gentle. The difference in gravitational pull between your head and feet would be barely noticeable. You could cross the event horizon and survive, intact, for minutes or even hours afterward. Ton 618, the behemoth? Its tidal forces at the event horizon would be so mild you might not feel anything unusual at all. You could theoretically survive crossing its event horizon and continue falling inward for nearly a day before tidal forces became lethal. This is the gravity paradox. The most massive black holes are the gentlest at their boundaries. The smallest are instant executioners. But there's another difference, equally profound and far stranger. What happens to time itself? According to Einstein's general relativity, the stronger the gravitational field, the slower time moves relative to an outside observer. Near any black hole's event horizon, time dilation approaches infinity. From the perspective of the universe, you would appear to freeze, never quite crossing that boundary, your light redshifting into oblivion. But from your perspective, time flows normally. You would cross the event horizon in finite time, your time. The difference between our three black holes isn't whether time dilation occurs, but how quickly you experience it. Near a stellar mass black hole, you'd be moving so fast, falling so steeply through such intense space-time curvature, that hours pass for distant observers for every second you experience. Near a supermassive black hole, the effect is there but gentler, perhaps minutes per second. And near Ton 618, you could fall for what feels like hours while millennia pass outside. But here's the haunting part. Time dilation affects not just your clock, but your perception of the universe itself. As you fall toward any event horizon, you would watch the cosmos accelerate. Stars would appear to speed through their life cycles. Galaxies would age. The very universe would rush toward its heat death before your eyes. The question becomes, which death is worse? Instant annihilation while the universe barely notices? Or hours of consciousness, watching eternity unfold, knowing you're already lost? But this discovery raised more questions than it answered. What would you actually see during such a journey? How does the appearance of spacetime itself change? And is there any way to understand these experiences without pure mathematics? Scientists first detected something extraordinary in their calculations of light behavior near black holes in the 1970s. At exactly 1.5 times the Schwarzschild radius of any black hole exists a phenomenon called the photon sphere, a region where spacetime is so warped that light can orbit the black hole in circular paths. For our 5 solar mass stellar black hole with a 15-kilometer event horizon, the photon sphere sits at 22.5 kilometers from the singularity. For Sagittarius A*, it extends to 18 million kilometers. For Ton 618, it stretches across 1,950 astronomical units. What makes this evidence crucial is what it reveals about visual distortion. If you approached any of these black holes from a safe distance, you would see the photon sphere as a luminous ring, light from stars behind the black hole, bent around its gravity into a perfect circle. But the size of this ring relative to your distance would differ dramatically. Near a stellar mass black hole, the photon sphere would snap into view suddenly as you approached, a thin, brilliant ring against darkness. Near a supermassive black hole, it would grow gradually, an expanding halo that could fill half the sky. Near TON 618, it would be so vast that you'd be inside the photon sphere region for hours before reaching the event horizon, surrounded by increasingly distorted images of the cosmos bent into impossible geometries. This is observable evidence that size fundamentally changes the experience of approach. In 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole shadow, M87 star, a supermassive black hole weighing 6.5 billion solar masses located 55 million light-years away. The image showed exactly what theory predicted, a dark circle surrounded by a glowing ring of light bent by gravity. What made this evidence powerful was its precision. The shadow measured 42 micro-arcsecons across, about the size of an orange on the moon as seen from Earth. This matched predictions from general relativity to within 4%. But here's what the measurements revealed. The gravitational lensing effect, the bending of light, extended far beyond the event horizon itself. Light passing within 3 times the Schwarzschild radius was significantly deflected. This creates what astronomers call the shadow, which is actually about 2.6 times larger than the event horizon itself. For a stellar mass black hole, this shadow region extends to about 40 kilometers. You'd have to be within this tiny sphere to see significant visual distortion. For Sagittarius A star, the shadow extends to 30 million kilometers, closer than Mercury is to our Sun. For TON 618, the shadow would span 3,380 astronomical units, 84 times the distance from the Sun to Neptune. What this means for a traveler: near a small black hole, the universe would look normal until suddenly, violently, it wouldn't. Near a supermassive black hole, the distortion would build gradually across millions of kilometers. Near TON 618, you'd spend weeks watching the universe slowly warp into stranger and stranger configurations. In active black holes, those feeding on nearby matter, we observe accretion disks, swirling torrents of superheated gas spiraling inward at near light speed, heating to millions of degrees and emitting X-rays we can detect across the galaxy. The innermost stable circular orbit, ISCO, marks where matter stops orbiting and begins its final plunge. For a non-rotating black hole, the ISCO sits at 3 times the Schwarzschild radius. Here's the critical evidence. Observations from NASA's Chandra X-ray Observatory and ESA's XMM Newton have measured ISCO positions for dozens of black holes. For stellar mass black holes, the ISCO is roughly 45 kilometers from the singularity. At this distance, orbital velocities reach half the speed of light. Matter orbits once every fraction of a second. The radiation is intense enough to vaporize any known material. For supermassive black holes, the ISCO extends to 36 million kilometers. Orbital periods stretch to minutes or hours. The radiation, while intense, is spread over such a vast area that certain regions might be theoretically traversable. Briefly, for TON 618, the ISCO would extend 3,900 astronomical units out. You could orbit at this distance for Earth weeks, spiraling slowly inward. The key evidence: size doesn't just scale the danger, it changes its nature from explosive to gradual. We don't need to visit a black hole to measure time dilation. We experience it daily, and we've measured it with exquisite precision. GPS satellites orbit Earth at about 20,000 kilometers altitude, where gravity is weaker than on the surface. According to general relativity, their clocks should tick faster than ours, about 45 microseconds per day faster. We've measured this effect continuously since GPS became operational, and the predictions match reality to within nanoseconds. This evidence matters because it confirms that time dilation isn't hypothetical. It's measured, real, and exactly as Einstein predicted. The equations that tell us GPS clocks run fast are the same equations that predict time dilation near black holes. Using these verified equations, physicists have calculated what you'd experience. Hovering at twice the Schwarzschild radius of a stellar mass black hole, an impossible feat requiring thrust equal to thousands of rocket engines, your clock would tick at about 60% the rate of someone far away. An hour for you would be 90 minutes for the distant universe. At twice the Schwarzschild radius of a supermassive black hole, the effect is gentler. Your clock ticks at about 85% the rate. Near TON 618 at the same relative distance, it's about 93%. But descend toward the event horizon, and time dilation grows without limit. At 1.01 times the Schwarzschild radius, just beyond the point of no return, time slows to a crawl. A second for you becomes minutes, hours, days for the outside universe. The evidence forces us to confront an uncomfortable possibility, that the universe you leave behind ages into incomprehensibility before you even realize you've crossed the threshold. But this is only one piece of a much larger puzzle. In 2018, astronomers using the Very Large Telescope in Chile tracked a star called S2 as it completed a 16-year orbit around Sagittarius A star. At its closest approach, S2 came within 17 light-hours of the black hole, about 120 times the event horizon's radius, and reached a velocity of nearly 8,000 kilometers per second, or 2.7% the speed of light. This observation provided evidence for something profound. Orbital mechanics near black holes follow different rules at different scales. To orbit stably at the ISCO of a stellar mass black hole requires a velocity of about 150,000 kilometers per second, half the speed of light. At this velocity, relativistic effects become dominant. Mass increases. Time dilates. Distances contract. You're not just in orbit, you're experiencing physics that has no earthly analog. To orbit at the ISCO of Sagittarius A star requires 84,000 kilometers per second, 28% light speed. Still relativistic, still extreme, but the effects are less pronounced. To orbit at TON 618 ISCO, roughly 10,000 kilometers per second, just over 3% light speed. Relativistic effects exist but remain relatively mild. You could potentially orbit for extended periods experiencing physics that, while extreme, remains comprehensible. This evidence reveals that black holes aren't just different sizes, they're different regimes of physics entirely. In 2012, physicists Joseph Polchinski, Ahmed Almhairi, Donald Merolf, and James Sully published a paper that shook theoretical physics. They argued that quantum mechanics, when combined with general relativity and the requirement that information cannot be destroyed, leads to an impossible conclusion. The event horizon might not be empty space at all. It might be a firewall, a region of extreme energy that would incinerate anything attempting to cross it. This contradicts Einstein's equivalence principle, which says that falling through an event horizon should feel no different than floating in empty space. The firewall paradox suggests that for large black holes, where the equivalence principle should hold most reliably, quantum effects might create a barrier that classical physics says shouldn't exist. Here's where it gets stranger for our three black holes. The firewall's temperature, if it exists, would be inversely proportional to the black hole's mass. For a stellar mass black hole, a firewall would have a temperature of trillions of degrees. For Sagittarius A star, billions of degrees. For TON 618, the firewall temperature drops to mere millions of degrees, still lethal, but orders of magnitude cooler. No one knows if firewalls actually exist. No consensus has emerged. But the possibility adds another layer to our paradox. Perhaps crossing any event horizon leads to instant annihilation, regardless of size. Or perhaps the firewall is unique to certain types of black holes. Or perhaps it doesn't exist at all. The evidence extends beyond classical physics into the realm of quantum mysteries we cannot yet resolve. In 1974, Stephen Hawking discovered something extraordinary. Black holes aren't entirely black. Quantum effects near the event horizon cause black holes to emit radiation, now called Hawking radiation, and slowly evaporate. The temperature of this radiation is inversely proportional to the black hole's mass. A stellar mass black hole emits Hawking radiation at about 0.00000001 Kelvin, far colder than the cosmic microwave background, which means these black holes actually absorb more energy than they radiate. They're growing, not shrinking. Sagittarius A star emits at 0.000000000002 Kelvin, incomprehensibly cold. Ton 618 radiates at 0.0000000000000001 Kelvin, a temperature so low it's nearly meaningless. At these temperatures, Hawking radiation is undetectable and irrelevant over time frames less than googol's of years. But the principle matters. It tells us that black holes have entropy, a measure of information content, proportional to their surface area. A stellar mass black hole has an entropy of about 10 to the power of 54 bits of information. Sagittarius A star contains 10 to the power of 91 bits. Ton 618 holds an almost incomprehensible 10 to the power of 107 bits. More information than exists in the entire observable universe by many orders of magnitude. This raises a haunting question. When you cross an event horizon, does the information that makes you get encoded on the horizon's surface? Are you somehow smeared across the boundary, experiencing both continuation and annihilation simultaneously? Recent calculations suggest that an observer falling into a supermassive black hole might survive long enough to notice quantum effects that smaller black holes would hide through simple lethality. In 2020, the European Space Agency's XMM Newton telescope observed something unprecedented: quasi-periodic oscillations in the X-ray emissions from an intermediate mass black hole in the galaxy NGC 1313. The oscillations had a frequency that precisely matched theoretical predictions for matter orbiting at the innermost stable circular orbit. What made this observation remarkable was its precision. The measurements confirmed that the ISCO exists exactly where general relativity predicts, and that matter falling inward from this point behaves as theory demands, accelerating to near light speed in mere seconds of travel. For our hypothetical journey, this evidence confirms a crucial fact. There's a point of no return before the event horizon itself. Once you pass the ISCO, no orbit is stable. You cannot circle. You cannot hover. You can only fall inward. For a stellar mass black hole, this happens at 90 kilometers from the singularity. For supermassive giants, it's much farther out but represents the same fundamental threshold. The final plunge from ISCO to event horizon would take different amounts of proper time for each black hole. For a 5 solar mass black hole, about 0.0001 seconds. For Sagittarius A star, about 20 seconds. For TON 618, roughly 8 minutes of subjective experience, watching spacetime fracture around you. The evidence forces us to recognize these are not 3 versions of the same experience. They are 3 fundamentally different encounters with gravity's ultimate expression. To understand what you'd actually experience approaching these 3 black holes, we must turn to the framework that predicted their existence. Einstein's general theory of relativity, published in 1915. General relativity describes gravity not as a force, but as the curvature of spacetime itself. Massive objects create wells in this 4-dimensional fabric, and other objects follow the straightest possible paths through the curved geometry, paths we perceive as orbits or falls. Carl Schwarzschild solved Einstein's equations for a perfectly spherical, non-rotating mass in 1916, just months after general relativity was published. His solution revealed the event horizon radius, the point where spacetime curvature becomes so extreme that all future paths lead inward. What Schwarzschild's metric tells us is precise. If you were to fall freely from rest at a great distance toward any black hole, your proper time, the time you experience, to cross the event horizon is finite and calculable. For a stellar mass black hole, microseconds from the ISCO. For Sagittarius A star, tens of seconds. For TON 618, several minutes. But here's what forces us to reconsider fundamental assumptions. From the perspective of a distant observer watching you fall, time appears to slow asymptotically as you approach the horizon. They would never see you cross. Your image would freeze, redshift to infrared and beyond, and fade from view. Both perspectives are correct. Time is relative. Your destruction is certain from your frame. Your eternal freezing is certain from theirs. This is not contradiction. This is spacetime curvature. In 1963, mathematician Roy Kerr discovered a more general solution to Einstein's equations, the metric for a rotating black hole. Since all stars rotate, and black holes form from collapsing stars, every real black hole likely rotates, some at appreciable fractions of the maximum possible rate. Rotation changes everything. It creates a region outside the event horizon called the ergosphere, where spacetime itself is dragged around the black hole. Inside the ergosphere, nothing can remain stationary. Everything must orbit in the direction of rotation, carried by the current of spacetime itself. For our three black holes, assuming significant rotation, the ergosphere would extend to about 1.4 times the Schwarzschild radius. This means a stellar mass black hole's ergosphere reaches to about 21 kilometers, a region you'd traverse in milliseconds at orbital velocities. Sagittarius A star's ergosphere extends to nearly 17 million kilometers, a region the size of Mercury's orbit where spacetime rotates. TON 618's ergosphere would span 1,820 astronomical units, a zone larger than the orbit of Sedna, the most distant object in our solar system, where the very fabric of existence whirls like a cosmic hurricane. The Kerr metric also predicts something extraordinary. Near a rapidly rotating black hole's ergosphere, an object could theoretically extract rotational energy from the black hole itself through a process called the Penrose mechanism. You could, in principle, throw an object into the ergosphere in just the right way, and have it emerge with more energy than it entered with, powered by the black hole's rotation. This theoretical framework suggests that supermassive black holes might not be simple cosmic drains, but complex dynamical systems with extractable energy. TON 618, with its vast ergosphere, might harbor physics we've never observed. Perhaps the deepest theoretical problem emerges when we combine general relativity with quantum mechanics. In quantum theory, information cannot be destroyed. This is a fundamental principle. But when something crosses an event horizon in general relativity, that information appears lost forever, hidden behind a boundary nothing can escape. This is the black hole information paradox, and after 50 years, it remains unresolved. Stephen Hawking originally argued that information is destroyed, violating quantum mechanics. Later, he suggested that information might be encoded in Hawking radiation, slowly leaking out as the black hole evaporates. More recent proposals involve holographic principles, the idea that all information about a three-dimensional region is encoded on its two-dimensional boundary. For our three black holes, the paradox manifests differently. A stellar mass black hole has a small surface area, about 2,800 square kilometers. The amount of information it can encode is limited. Sagittarius A star has a surface area of 1.8 trillion square kilometers, roughly 3,500 times Earth's surface. TON 618's surface area reaches 212 quadrillion square kilometers, about 20 million times Earth's surface. If information is somehow encoded on the horizon, then larger black holes can store vastly more quantum information. Does this mean that falling into a supermassive black hole somehow preserves you in more detail than a stellar mass black hole could? Or does the information encode only the fact that something fell in, not its detailed structure? These questions remain at the frontier of theoretical physics, investigated at institutions like the Institute for Advanced Study, Caltech and Cambridge. the answers might tell us something fundamental about the nature of reality itself. Recent breakthroughs suggest we're on the verge of observing black holes with unprecedented detail. The Event Horizon Telescope, which captured the first black hole image in 2019, is expanding. New telescopes in Greenland, Chile, and Africa will increase its resolution by a factor of 10, potentially allowing us to observe matter at the innermost stable circular orbit, the point where physics becomes truly extreme. NASA's upcoming Laser Interferometer Space Antenna, LISA, planned for launch in the 2030s, will detect gravitational waves from supermassive black hole mergers across cosmic time. When two supermassive black holes collide, they emit gravitational waves for weeks or months before merger, allowing us to observe the approach, circling, and final coalescence in exquisite detail. These observations will test general relativity in strong field regimes no experiment can replicate. The Nancy Grace Roman Space Telescope, scheduled for 2027, will survey millions of stars in our galaxy's core, tracking their orbits around Sagittarius A star. By mapping orbits with unprecedented precision, astronomers will measure the black hole's mass and spin to new accuracy, testing whether general relativity correctly predicts orbital mechanics in intense gravity. Most ambitiously, theoretical proposals exist for placing an interferometer in space with baselines of thousands of kilometers, dwarfing anything ground-based. Such an instrument could resolve the event horizons of supermassive black holes in dozens of nearby galaxies, mapping them with sufficient detail to test competing theories of quantum gravity. Each of these missions will refine our understanding of what happens at black hole boundaries, providing evidence that either confirms or challenges our theoretical predictions. One of the most exciting developments concerns the potential observability of quantum effects at event horizons. If firewalls exist, they would emit detectable radiation, potentially distinct from normal Hawking radiation. The challenge is that this radiation would be extraordinarily faint and mixed with emissions from the accretion disk. A 2022 proposal by physicists at MIT suggests using interferometry to look for subtle correlations in the radiation from near-event horizons, quantum entanglement signatures that would reveal whether the horizon is smooth spacetime or something more exotic. Such measurements require sensitivity beyond current instruments but might become feasible in the 2030s. For supermassive black holes, these quantum effects should be relatively strong per unit area compared to stellar mass black holes. TON 618, despite its size, might be one of the best laboratories for testing quantum gravity predictions precisely because its vast event horizon amplifies subtle quantum effects into potentially detectable signals. Future breakthroughs could tell us whether the gentle crossing predicted by general relativity is correct, or whether quantum mechanics imposes a lethal barrier that classical physics cannot predict. The study of black hole approaches has implications far beyond understanding these specific objects. They represent the most extreme gravitational environments in the universe, natural laboratories where spacetime curvature reaches its limit. Understanding time dilation near black holes has practical implications for any future civilization attempting to manipulate spacetime. If humans ever develop technology to create controlled gravitational fields, the physics of black hole environments provides the theoretical foundation. Time dilation could theoretically be used for time travel to the future. Orbit close enough to a black hole's ISCO, and when you return, centuries might have passed. The tidal forces near stellar mass black holes reveal the limits of material strength. No known or theoretically possible material could withstand the tidal stresses within 1,000 kilometers of such an object. This defines an absolute boundary for engineering. Some places in the universe cannot be visited by any physical structure, regardless of technology. Conversely, the gentle environment near supermassive black hole event horizons suggests that with sufficient technology, one could theoretically approach, study, and even orbit very close to such objects. Automated probes might one day cross the event horizon of a supermassive black hole, transmitting data up until the final moment of communication. Most profoundly, black holes represent the intersection of general relativity and quantum mechanics, the two pillars of modern physics that have resisted unification for a century. Any theory of quantum gravity must correctly predict what happens at black hole event horizons. Observing these regions, even indirectly, provides crucial tests that could guide us toward a complete theory of the universe. The human significance is clear. Black holes aren't just cosmic oddities. They're cosmic teachers, showing us the limits and possibilities of physics itself. In studying them, we study the fundamental structure of reality. The most profound implications emerge when we consider what you would actually experience during the final approach to each black hole. Near a 5 solar mass stellar black hole, your final moments would be violent and brief. As you cross inside the ISCO at 90 kilometers, tidal forces would already be significant, thousands of G's differential across your body. You'd be pulled into an elongated shape, blood pooling toward your feet, bones beginning to crack. Within milliseconds, the differential would exceed millions of G's. Your molecular bonds would fail. You'd dissociate into a stream of atoms, then subatomic particles, crushed to infinite density as you approach the singularity. From your perspective, if consciousness could somehow persist, you'd see the universe above you blue shifted to gamma rays, a brilliant point of light containing all of cosmic time accelerated. Below, infinite darkness. The process from ISCO to singularity would take perhaps 0.0001 seconds of proper time. You would not have time to understand what was happening. Near Sagittarius A star, the experience transforms into something stranger. Crossing the ISCO at 36 million kilometers, tidal forces would be negligible, perhaps a few G's, uncomfortable but survivable. You'd fall for about 20 seconds of proper time before crossing the event horizon at 12 million kilometers. During this fall, you begin to notice optical effects. Light from distant stars would concentrate into a shrinking circle behind you, while darkness expanded ahead. Time dilation would become noticeable. Every second you experience corresponds to minutes or hours outside. The event horizon crossing itself would be unremarkable from your perspective. No sign, no barrier. Spacetime remains smooth. You'd continue falling for perhaps another minute before tidal forces, growing as you near the singularity, finally became lethal. In your final seconds, you'd watch the universe above age rapidly, stars dying, galaxies colliding, deep time unfolding in moments. You'd have time to understand, to contemplate, to say goodbye to a cosmos you can see but will never rejoin. Near Tiawan 618, the experience becomes almost contemplative. Crossing the ISCO at 3,900 astronomical units, farther than Sedna orbits our Sun, tidal forces would be imperceptible. You could be in a spacecraft, floating freely, with instruments reading perfectly normal conditions. You'd fall for roughly 8 minutes of proper time before crossing the event horizon at 1,300 astronomical units. The event horizon crossing would be completely undetectable. No instruments could tell you've passed it. You'd continue falling for potentially an hour or more, still experiencing only gentle acceleration, still able to observe the cosmos. The universe above would age noticeably but not catastrophically, decades or centuries per minute of your time. You'd watch stars evolve. You might see supernovae, gamma ray bursts, the slow dance of cosmic evolution. Only after an hour of falling would tidal forces begin to approach lethal levels, and even then, the growth would be gradual, giving you minutes of warning. In those final minutes, you'd have time to record observations, to understand the physics of your situation, to contemplate the nature of the cosmic fate you're experiencing. 3 black holes. 3 completely different encounters with the same fundamental physics. Same laws, radically different experiences. But consider now the opposite perspective, someone watching you fall from a safe distance. As you approach any black hole, they would see you slow down, asymptotically approaching the event horizon but never quite reaching it. Your clock would appear to slow. Your movements would become sluggish. Light from you would redshift, first to infrared, then radio waves, then effectively disappear. For a stellar mass black hole, this process would appear to happen quickly. Within seconds from their perspective, you'd fade from view, frozen at the horizon's edge forever in their reference frame. For Sagittarius A star, the fade-out would be more gradual. Minutes of watching you slow, redshift, and vanish. For 2 and 618, they might watch for an hour as you descend, your signals weakening, your image increasingly ghost-like, until finally you're simply gone. Still theoretically frozen at the horizon from their perspective, but observationally indistinguishable from having vanished completely. This creates a profound philosophical paradox. From your frame, you cross the horizon and die at the singularity. From their frame, you never cross at all. You're frozen forever at the boundary, your information smeared across the event horizon's surface. Both are correct. Both describe the same physical reality. There is no absolute answer to what really happens. This is general relativity's most unsettling implication. Reality itself is observer-dependent at the most fundamental level. Let us confront the final question: what awaits at the singularity itself? General relativity predicts that at the center of every black hole lies a singularity, a point where spacetime curvature becomes infinite, where density becomes infinite, where the equations of physics break down completely. But point is perhaps misleading. In a rotating black hole, the Kerr solution predicts a ring singularity, a circle of infinite density. What happens when you reach this? The mathematics simply fails. General relativity provides no answer because it's asking a question beyond its own domain. Quantum mechanics must govern here, but we have no tested theory of quantum gravity. Some proposals suggest the singularity isn't a point of infinite density but rather a region where spacetime itself becomes quantized, broken into discrete units at the Planck scale, roughly 10 to the power of -35 meters. At this scale, the concepts of space and time might cease to have meaning. You wouldn't be crushed to a point. You'd encounter some kind of quantum boundary where the rules of physics as we know them simply don't apply. Other proposals, like loop quantum gravity, suggest that the collapse might be halted by quantum pressure, creating a Planck star, an object of enormous but finite density that could theoretically bounce, creating a white hole on the other side. You might not be destroyed at all, but transported somewhere. Another region of spacetime, another universe, who knows? String theory proposes that black hole singularities might be replaced by fundamental strings or brains vibrating in higher dimensions, structures that have no classical analog but obey quantum rules that prevent true infinities. The honest answer is, we don't know. We cannot know without a theory of quantum gravity, and we have no way to test such theories observationally. The singularity remains hidden behind the event horizon, causally disconnected from our universe, forever beyond our ability to observe. But here's what we can say with confidence. Whether the singularity is a point, a quantum foam, a Planck star, or something else entirely, reaching it marks the absolute end of your causal relationship with the universe you came from. No signal can escape. No information can return. Whatever happens there is, quite literally, beyond the realm of physics as practiced by any external observer. For our three black holes, the singularity represents the same ultimate mystery, but the journey to reach it differs by orders of magnitude in duration, intensity, and phenomenology. Same destination, three radically different paths. We began with a paradox, that the largest black holes are the gentlest, and the smallest are the most violent. We've journeyed through the evidence, from gravitational lensing to time dilation measurements, from accretion disk observations to the theoretical frameworks that predict them all. What have we learned? That black holes are not monolithic objects but exist on a spectrum of experience. A stellar mass black hole offers instant annihilation, too fast for consciousness to register. A supermassive black hole allows minutes of awareness, time enough to understand your fate and watch the universe age. The largest black holes permit hours of contemplation in what appears to be gentle free fall, punctuated only at the end by the same inevitable crushing. We've learned that time itself is relative in the most profound sense, that two observers can witness the same event and see completely different outcomes, both correct, neither privileged. We've seen that general relativity's predictions match observation with stunning precision, yet leave us with paradoxes that demand quantum gravity for resolution. We've discovered that these objects, once thought to be simple points of darkness, are actually the universe's most complex gravitational systems: rotating ergospheres, photon spheres, infinite time dilation, quantum firewalls, information paradoxes. They're where Einstein meets Heisenberg, where classical physics confronts its own limits. Science currently knows this. Black holes exist, they have measurable properties, and their effects on spacetime match general relativity's predictions wherever we can test them. Approaching any black hole means experiencing time dilation, tidal forces, and visual distortion, effects that scale dramatically with size. Science still cannot answer what happens at the singularity, whether firewalls exist, how information is preserved, or what quantum gravity truly predicts for these extreme conditions. These questions remain open, awaiting future observations and theoretical breakthroughs that may come next decade or next century. The gravity paradox teaches us humility. The universe contains phenomena so extreme they transcend human intuition. Size doesn't make them more or less dangerous, it transforms the nature of danger itself. And somewhere in the mathematics of curved spacetime and quantum fields lies a deeper truth about reality we have yet to grasp. 3 black holes. 3 journeys to oblivion. 3 windows into physics at its most fundamental and least understood. The monsters we fear most might be the gentlest. The deaths we imagine might take forms we cannot anticipate. And the universe, vast and strange, continues to hold mysteries that challenge everything we think we know. The journey continues. The questions endure. And somewhere in the darkness between event horizons, the answers wait.